Hi, today I want to show you how to use some of the Core Independent Peripherals on the AVR Tiny1 series to create an extremely power efficient solution for controlling an LED such that it mimics a heartbeat pulse. Once initialized, Core Independent Peripherals are functional hardware blocks designed to handle specific tasks with no code or supervision from the CPU. Because the peripheral functionality is deterministically and reliably performed in hardware instead of software, they enable system performance that is far beyond typical microcontroller units. Another benefit is that the design experience is simplified while having the potential to both optimize the memory and power budget of an application. In other words, the method will work 100% independently of the CPU after the initial setup, allowing the CPU to either sleep or do other important tasks with true hardware parallelization. We'll go through and compare 3 different implementations of a heartbeat LED example to illustrate the possible benefits of utilizing the core independent functionality of the ATtiny817. The first implementation is a simple busy wait solution. The second is a more traditional approach using periodic interrupts, while the third is the core independent solution. Before going through how to actually implement the most efficient alternative, I will present the working principle behind the solution. Finally, I'll show you some performance measurements, including the current consumption and code size for each example. As we will see, the core independent solution will use 50 times less current on average, while consuming 4 to 5 times less of the program memory compared to the other 2 approaches. All the solutions will be run on the ATtiny817 Xplained Pro development kit, but will work on any device in the Tiny AVR 1 series. All source code used in this video is available in the description below. First, let's briefly go through how we increase or decrease the light intensity of an LED for those of you who are not familiar with the concept. Here you see a simple illustration of a Tiny817 microcontroller. It shows the CPU and the timer counter A peripheral, or TCA for short. We can configure TCA to output a pulse width modulated signal, or PWM signal for short, on an I/O pin connected to an LED by defining an init PWM function. We can then define another function to set the duty cycle of that signal. Calling the init function will turn on the LED. Increasing the duty cycle will increase the brightness of the LED, while decreasing the duty cycle will decrease the brightness. Now we can take a look at the simple busy wait solution. Here we start with a for loop that increases the duty cycle in each loop to a certain point. Between the duty cycle updates, we run a busy wait or delay function to ensure that the updates happens periodically at a desired rate. We then decrease the duty cycle in the next for loop to some specified low value before increasing it to a larger value again, and finally decreasing it to 0. Then we wait for a while. By placing this sequence inside an infinite while loop in the main function, we periodically repeat the heartbeat pulse. The values of the delays are configured such that it takes 1 second to go through the while loop, which yields a 60 beats per minute heartbeat pulse. This simple implementation certainly produces the desired output, but the CPU is spending 100% of its resources on this task alone, while wasting power busy waiting. A more efficient and perhaps common approach is using periodic interrupts to modify the duty cycle. Instead of busy waiting between the updates, we can configure another low-power real-time counter peripheral, or RTC, to enable a periodic interrupt timer with a init RTC PIT function. Here we use the RTC because generating interrupts from TCA would result in too frequent interrupts for our purpose. This periodic interrupt can then trigger an interrupt service routine, or ISR, which can call an update heartbeat function to increase or decrease the duty cycle appropriately. We can then define a state machine that consists of the 5 states of one heartbeat pulse: rising small, rising big, falling big, and a waiting state, which eventually will transition to the beginning. In the update heartbeat function, we use a switch case on the current heartbeat state. Each time the function is called with the rising small state, we want to increase the duty cycle variable up to a desired value before transitioning to the next state. We also make sure to update the duty cycle with the new value after the switch case at the end of the function. We continue to configure each case to produce a similar output as the busy wait solution. The interval of the periodic interrupts is also chosen to produce a 60 beats per minute heartbeat pulse. In this way, the CPU can go to sleep or do other important tasks between the duty cycle updates. Despite this, waking up the CPU and going to sleep several times each second can still be unnecessarily energy consuming, or the periodic interrupts could be interfering with other real-time tasks. To improve on this implementation, we can use Core Independent Peripherals to reduce the energy consumption and free up the CPU. Before showing the example though, an explanation of the working principle behind the implementation is necessary. Say you have two square wave signals A and B with the same duty cycle but with different frequencies FA and FB. Notice how the difference in frequency causes the signals to drift relative to each other over time. Now imagine continuously performing a Boolean AND operation between these two signals. This drifting will cause the duty cycle of the output to first increase and then decrease over time as the active high part of A and B overlap to a greater or lesser extent. This periodic sequence where the duty cycle is dynamically increased and then decreased will be repeated with a frequency that is equal to the difference in frequency between FA and FB. This fact can be used to create a pulsating PWM output, where we can control the pulse frequency or period by carefully selecting the frequency of the two input signals. If one of the input signals have a small duty cycle, while the other has a larger duty cycle, then the maximum duty cycle value of the output will be equal to the small duty cycle value. The larger duty cycle will then determine how long the output signal will maintain the maximum duty cycle value before it starts to decrease again and stay at zero for a while. In other words, the smallest duty cycle determines the maximum light intensity, and the larger duty cycle determines the length of the pulse. Since we want the heartbeat pulse to consist of two pulses with different light intensity, we have to add a third PWM signal. In this implementation, the first two signals, which we call A1 and A2, have the same frequency FA, but one has a small duty cycle and the other a larger duty cycle to achieve a small and a large pulse. Since we want the small pulse first, followed immediately by the larger pulse in the heartbeat signal, we can phase shift A2 with a distance that is equal to the duty cycle of a third PWM signal, which we call B. Signal B has a different frequency FB. Since A1 and A2 have the same frequency, they will not drift relative to each other, while signal B will first increasingly overlap with A1, then decrease in overlap, before starting to overlap with A2, and finally no overlap for a while. If we do a Boolean AND operation between B and A1 XOR A2, we produce a heartbeat-like output. Here, the duty cycle of A1 determines the maximum light intensity of the small pulse, while the duty cycle of B determines the length of the small pulse. In the other case, since the duty cycle of B is smaller than the duty cycle of A2, it is the duty cycle value of B that determines the maximum light intensity of the second pulse, while A2 determines the pulse width. This heartbeat pulse will repeat with a specific beats per minute equal to FA minus FB times 60. Given that FA is greater than FB. So, for instance, if we choose FA equals to 101 Hz, FB equals to 100 Hz, the resulting beats per minute will be 60. Before comparing the power and memory consumption of this approach to the other two, we will go through how to implement it using the online Atmos Start tool, where this example is freely available. To create the PWM signals, we can use timer counter B or TCB and timer counter D or TCD, as they will remain active during the idle sleep mode where the CPU is turned off. TCD can generate two PWM signals with the same frequency but with a different phase and duty cycle, representing signal A1 and A2, while TCB generates one PWM signal with another frequency and duty cycle, which we call signal B earlier. Once the PWM signal properties are configured such that a desired beats per minute and pulse width is achieved, we can combine the signals by using the Configurable Custom Logic or CCL peripheral on the device. This peripheral allows for up to 3 signals to be routed through one of the configurable truth tables. The table is implemented as a programmable lookup table in the hardware and can be configured in Start using Boolean notation. Here we do an AND operation between C and A XOR B, where the output is inverted since the LED is low side driven. The output is then further routed to an output pin connected to the LED. The same result can also be achieved by programming the device bare bones and manipulating registers directly, but using Atmel Start simplifies the process. From here we export the project into Atmel Studio, making sure the CPU is running the necessary initialize function generated by Start, and set the system in the idle sleep mode, making the CPU shut down completely while the configured core independent peripherals remain active. Finally, we build and run the solution on the device. Now we have created an application where an output pin will produce a PWM signal with a varying duty cycle that makes the LED pulsate in a heartbeat-like fashion 100% free of the CPU. By connecting my custom LED array to the same output pin, the effect is made a bit more exciting. From here we can also create a function to change the beats per minute and/or pulse width of the heartbeat during runtime. Now let's take a look at some performance measurements. Inspecting the code size for each example, we can determine that the busy wait solution uses 13% of the program memory on the device, while the periodic interrupt solution uses 16%. By contrast, the core independent solution only uses 3%, which is a 5 times improvement compared to the periodic interrupt solution. By using the built-in power measurement tool on the Xplained Pro development kit, we can measure the current consumption of the device without the LED and other external circuitry, and visualize it using the data visualizer in Atmel Studio. All the implementations measured here are optimized for low power consumption by setting all I/O pins as input with pull-up enabled and lowering the system clock frequency as much as possible. The measurements show that the busy wait solution consumes 464 microamps on average. The periodic interrupt solution is a bit more efficient, using 449 microamps on average. Even though the CPU is sleeping between the duty cycle updates, it still has to wake up rather frequently, and here we are also using an additional hardware peripheral compared to the busy wait solution. The core independent solution has a dramatically lower current consumption of only 8 microamps on average. That is over 50 times better than the interrupt solution. Moreover, if we consider a use case where the microcontroller is powered with a small 200 mAh coin cell battery, it will take about 18 days to drain the battery for both the busy wait and interrupt solution. In comparison, the core independent solution can run for almost 3 years before draining the battery. This is achieved by completely shutting down the CPU and using the ultra-low power 32 kHz clock source as the system clock, which is not possible for the 2 other examples as it is too slow to meet the update deadlines. Not only does the core independent solution save power compared to the other implementations, but the CPU is free to sleep or do any other tasks in an application as well. All 3 power-optimized examples are available from our example code repository on GitHub, which is linked in the description. The normal core-independent heartbeat example is also available on GitHub with both a Start driver-based project and a bare metal project for both MPLAB X and Atmel Studio. These examples also include a function for changing the beats per minute during runtime by changing some of the timer counter settings. This function can alternatively be used to pre-calculate the correct timer counter register values for a specific beats per minute for the heartbeat pulse before compiling the program. We hope you have enjoyed this video and hopefully learned something about the core independent peripheral functionality of the Tiny AVR 1 series. Thank you for watching.